Good afternoon everyone. Welcome to the week 4 problem solving session for pattern recognition and application course. I am Tanuka Bhattacharjee. I am a PhD student in the electrical engineering department at IISc. So as in the last problem solving session, we solved several problems from Bayesian decision rule and discriminant functions. So today we will take up one more problem from discriminant functions or decision surface related problem, and then we will move on to parametric probability density estimation, particularly the maximum likelihood estimation based problems. So let us get started with our first problem for today. So you can see that the problem says that it is a 2-class problem. We are concerned with a 2-class problem. The classes are omega 1 and omega 2. Omega 1 and omega 2, and we have d-dimensional binary feature vector. So the entire feature vector, if I denote it by capital X, this is basically has d components, small x1 to small xd, and each of these component is a binary feature. So if I say xi can take only binary values, so it can be either 0 or 1. So we have a d-dimensional binary feature vector, and it is also given that ai is the probability that xi equal to 1 given the class is omega 1. So if the feature vector belongs to class 1, then its ith element being 1, that probability is given by ai. And similarly, bi is the probability that when the feature vector belongs to class omega 2, then the probability of the ith element of the feature vector being 1 is given by bi. So these are kind of the class conditional densities are specified by these parameters ai and bi. Now it is said that assume all the features are statistically independent and the classes are equiprobable. That means the prior probabilities are equal, that is p of omega 1 equals to p of omega 2. Then we have to say which of the following corresponds to the equation of decision surface. So we will proceed using the discriminant function approach that we know. So let us say g1x is the discriminant function for class 1 omega 1, and g2x is the discriminant function for class omega 2. So they have asked in the question that we have to determine the equation of the decision surface. So as you know, on the decision surface, the value of the discriminant function for both the classes will be equal. So if we want to find the decision surface, then at that surface g1x will be g2x. The value of discriminant functions of both classes will be equal, or you can say g1x minus g2x equal to 0. Now you also have seen that the g1x is suitable to take log of the posterior probability. The log helps us in computation. So we can take this as ln of p omega 1 given x, that is the posterior probability of class omega 1 given x. The log of that probability is our discriminant function for class omega 1. So the class which will have the higher value of the discriminant function, you will classify the feature vector in that particular class. Now we also know that by Bayes rule we can write p omega 1 given x as px given omega 1 into p omega 1 divided by p of x. Right. So if I write in this g1x equal to g2x expression, so it will become ln of p x given omega 1 into p omega 1 by p of x equal to ln of px given omega 2 into p omega 2 divided by px. Now px is a positive number which is present on both sides, so we can safely cancel it from both sides. In that case, the expression becomes ln of px given omega 1 plus ln of p omega 1, that will be equal to ln of p x given omega 2 plus ln of p omega 2. Now the question is, how will you write px given omega 1 or px given omega 2? So it is mentioned in the question that given omega 1, the probability of an element xi being 1 is ai. So we can write the conditional density in a general form as we can write it like this: ai to the power xi into 1 minus ai to the power 1 minus xi. This term, product of all this term for all I 1 to d. This gives us the general expression for the class conditional density for class omega 1, because ai is the probability that xi is 1 and 1 minus ai will similarly be the probability that xi is 0. So in general you can write this particular expression. So if we put this expression here, it is basically plus ln of p of omega 1, that is equal to ln of product of I equal to 1 to d. I am writing the class conditional density for the class omega 2 similarly, where ai will be replaced by bi, because there the probability of xi being 1 is given by bi. So the expression will be bi to the power xi into 1 minus bi to the power 1 minus xi. Okay. Plus we have the ln p of omega 2. Now we can expand the ln terms or simplify the ln terms. The product will become a sum I equal to 1 to d xi ln ai plus 1 minus xi ln 1 minus ai. This entire thing is within the summation, plus ln of p omega 1. That is equal to, if we similarly simplify the right hand side, becomes summation I equal to 1 to d. Here it will be xi ln of bi plus 1 minus xi ln of 1 minus bi plus the prior probability term. This is the simplified expression. Now you see the first term in the summation on both sides have the term as xi, and the second term has 1 minus xi. So we can club the terms with xi together and the ones with 1 minus xi together, and the remaining two prior probabilities together. That will make it summation I equal to 1 to d xi ln of ai by bi plus 1 minus xi ln of 1 minus ai by 1 minus bi. This entire thing is in the sum, plus ln of p of omega 1 by p of omega 2 equal to 0. So this is the simplified expression for our decision surface. So if we match with our options given here, you see in option B we have summation I equal to 1 to d xi ln of ai by bi plus 1 minus xi ln of 1 minus ai by 1 minus bi plus ln of p omega 1 by p omega 2 equal to 0. So this is the expression that we got. Now here it is again given that the classes are equiprobable. So p omega 1 is equal to p omega 2. So this ln of p omega 1 by p omega 2 term will actually become 0, and we will get the expression given in option A. So if we are trying to write the expression for a general prior probability, then option B is that answer. So it is valid here also, but since we have the further information that the two classes are equiprobable, we can further simplify this expression, and on simplification we got the expression as the option A. So this is basically the equation of decision surface in this particular case. Okay. Now let us move on. This was our last problem on the discriminant function based approach. Now we will move on to the parametric probability density estimation, or in particular we will try to solve some problems on maximum likelihood estimation. So let us look at the first problem. Here it says that x is a discrete random variable and its mass function is given as f x given p equal to 1 minus p to the power x minus 1 into p, and x can assume values 1, 2, 3, 4 like that. So all positive integers x can take, and here p is the parameter. The value of p is greater than 0 and less than 1. So this is basically the geometric distribution. So we have to tell what is the ML estimate or the maximum likelihood estimate of p. Okay. So this is the probability mass function, the parametric form of the probability mass function that we have, the f x given p, where p is the parameter. So for maximum likelihood estimation, let's say we have the data set D, which contains n number of observations of capital X, which are x1, x2 to xn. We have this particular data set, x1 to xn, n number of observations we have, and this constitutes the data set D. So first step in estimating the ML estimate of P is to find out the likelihood of this particular data set. So what is that? That is, we denote that by probability D given P. Here we are using the notation given P, since P is the parameter. Given P, the distribution is specified. So we are estimating the probability of the data set D given the parameter is P. Now here we assume one more thing, that this data set x1 to xn, these are basically independent samples and identically distributed. So these are basically IID samples, independent and identically distributed. So if you take any particular x1, the probability of that particular x1 or xi will be 1 minus p to the power xi minus 1 into p. Now since all these x1, x2, xn are independent, so to get the joint probability we can simply take the product. So the likelihood of this particular data set, or the probability of observing x1 to xn given that the parameter for this distribution is p, is given by product of I equal to 1 to n 1 minus p to the power xi minus 1 into p. This we can write because the samples are independent. So, we can take the product of each of their probability to get the joint probability of their occurrence, of the occurrence of the entire data set. So, this is our likelihood. Now, in ML estimate, we generally take the log likelihood. That simplifies the calculation a lot, because here also you have the product. As soon as you take the log, it becomes summation, then the further calculations become much easier. So, we will take the log likelihood for the parameter p. We denote that by small l, which is a function of p, and we write that as, basically this is ln of p d given p. So, that is, if we apply log on the right hand side, we get summation I equal to 1 to n xi minus 1 ln of 1 minus p plus ln of p. The entire thing is within the summation. Okay. Now, what do you do in ML estimate? So, you try to find the estimate for p which corresponds to the maximum likelihood of this particular data set. So, we try to maximize this log likelihood. That is, we try to take the derivative of this log likelihood with respect to p and we equate that to 0. So, basically we take the derivative with respect to p for L of p and we make that 0, and that value corresponds to our estimate of p. So, if we do that, so our log likelihood is given by this expression. Let's write it down once more. Sorry, this is okay. Now, we take the derivative with respect to p. That will give us summation I equal to 1 to d. The term xi minus 1 remains as it is. Ln of 1 minus p, this term gives the derivative minus 1 by p, 1 by 1 minus p. So, minus 1 by 1 minus p plus ln of p gives 1 minus p. So, this we equate this to 0. Now, if we simply do some simplification steps, we get oh sorry, this was n not d. I'm really sorry, it was we chose the number of samples as n, I miswrote it as d. The summation should be I equal to 1 to n everywhere. It should not be d, because we do not have d here. It is just a single dimensional feature vector and the number of samples is basically n. So, this will be n. This is equal to 0. That is, you can write the second term is 1 by p summation I equal to 1 to n over 1. So, this basically is n by p. So, if you take n by p and take the first term on the other side. This is this. Now I will do some side change. This is basically equal to 1 by p minus 1. The right side is the same. If I take further the 1 on this side, then 1 by p becomes 1 p becomes 1 plus 1 plus 1 by n summation xi minus 1. You can further simplify this. So this is basically 1 by n summation I equal to 1 to n xi minus 1 by n into n, because here is also there is a summation I equal to 1 to n over 1, so that will give rise to n, and we have 1 by n. So this will basically become 1 by n summation I equal to 1 to n xi. So finally p will be the inverse of this 1 by this, so it will be n by summation I equal to 1 to n xi. So this is the maximum likelihood estimate of p. Okay. This is the final answer. Okay. Let us see one more problem on this particular topic, the maximum likelihood estimation. Here also we are taking x as a discrete random variable, and the mass function is given by this particular expression, and here you can see that x can take values only -1 and +1, nothing else. It can just assume two values, either -1 or +1, and this is the expression. So you can see if x takes the value 1, if x takes the value 1, then that probability is p, and the x taking the value -1, that probability is 1 minus p. This is basically like a Bernoulli distribution, where the x can assume the values -1 and 1 instead of 0 and 1. And here also p is the parameter. So we will have to find out the ML estimate for p. So here also we will first determine the likelihood of this data set p d given p. D is the same set of n observations of x, x1 to xn. So this will become as before. This is our data likelihood. Now we will compute the log likelihood, because here also we have product of multiple terms, and if we take the log, that will become summation, and taking the derivative will be much easier. So the log likelihood L of p will become I equal to 1 to n 1 plus xi by 2 ln of p plus 1 minus xi by 2 ln of 1 minus p. This is within the summation. Now we need to maximize this log likelihood. So we will take the derivative of this log likelihood with respect to p and equate that to 0. So if we take the derivative with respect to p, what we get is summation I equal to 1 to n 1 plus xi by 2 into 1 by p plus 1 minus xi by 2 into minus 1 by 1 minus p. We equate this to 0. Now if we solve this, what value will get for p? That will be the ML estimate for p. So let us solve. I can take 1 by 2p out here. This is equal to 0. This is equal to 0. So I'll put the 2 on two sides. So this is the expression we get. We can simply cancel 2 from both sides and take 1 minus p on this side. So that will become So again, as in the previous problem, we can further simplify this summation terms. So if we expand this, this is basically x. So the first term, which is the summation of 1 over I equal to 1 to n. So this is basically we are adding n 1 for n times. So we will get 1 n minus summation of xi over I equal to 1 to n, and in the denominator similarly we have n plus summation I equal to 1 to n xi. Now this is the left hand side, we can further write it as 1 by p minus 1. So if we take that minus 1 to the other side, it will become like this. I'm just not writing the limits of the summation. Now if we simplify this, this becomes So we have the same summation terms with plus sign and minus sign, summation over xi I equal to 1 to n. So these two terms cancels out. So finally we have 2n by n plus summation xi. Okay. So if we want to get p, that will become n plus summation xi by 2n, n plus summation xi by 2n, and the summation you can further write it as So, this is the final maximum likelihood estimate for P. For the case of Bernoulli distribution where x can take the values -1 and 1. Okay, this is the general procedure for estimating maximum likelihood estimates. So, you basically first take the data likelihood, which you determine for a data set of independent samples. So, you basically just take the product of the probability of each sample, that is your data likelihood. Then you go into log likelihood to simplify the computation. Once you have log likelihood, your all product terms become summation. Now, you need to maximize this log likelihood. So, you take the derivative of this log likelihood with respect to the parameter. So, here P was our parameter. So, we take the derivative with respect to P, and then you equate this log likelihood derivative to 0, and you get this estimate as the maximum likelihood estimate or ML estimate of P. So, these were examples of ML estimate for two different probability mass functions. You can compute it for any parametric distribution or density function. Now, let us move on to the next problem. Next, we have the exponential distribution, where the probability of x is given by lambda e to the power minus lambda x if x is greater than equal to 0 and it is 0 otherwise. So, here you can see that this is also a parametric density function, and the parameter here is lambda. So, once you specify the value of lambda, this density function is completely specified. You do not have any other parameters. Lambda is the only parameter. So, if you can estimate the value of lambda from your data set, you have completely estimated this density. Now, it is said here that let us say mu is the mean of the samples, or mu is the mean of this particular density function. Then, what is the relation between mu and lambda, that we need to determine. So, how we will approach this problem is, we will try to determine the expression for mu. So, once we have the expression for mu, we will try to we will have some expression in terms of lambda, and we will try to determine the relation of lambda and mu from there. So, as you know, the mean is basically the expectation. So, you can compute mu, the mean of the samples, as the expectation of this particular distribution or expectation of this exponential distribution. That will give you the mean of this distribution or mean of the samples. And we write expectation as E of x, and as you will know, the formula for computing expectation is integration minus infinity to infinity x px dx, where px is the value of the PDF function at x. So, this expression is integration minus infinity to infinity, that is for all values of x, we need to do x px and integrate it over x. This is the expression or formula for computing expectation. So, in this case, as you can see that if x is greater than equal to 0, then we have some value of the density function, otherwise that density function is 0. So, px will be 0 when x is less than 0. So, we can simply change the limit of this integration to 0 to infinity, because before that this term will be 0. X, and when you have x greater than equal to 0, then your px is given by lambda e to the power minus lambda x. Lambda e to the power minus lambda x dx. So, this will be the expression for our expectation. Now, we take the lambda out, x e to the power minus lambda x dx. So as you can see, you have to solve this integration by parts approach. So x will be one part and e to the power minus lambda x will be the other part. So we can do this integration like this. Lambda we keep it outside. Then for the integration part, first we take the first function into integration of second function, that is e to the power minus lambda x. Integration will be e to the power minus lambda x by minus lambda. This we will put the limit as 0 to infinity. This is first function into integration of second function minus integration differentiation of first function, that is differentiation of x will be 1, then integration of first function, that is again this thing. So this becomes the simplification by integration by parts. Now if we put the limits, so it becomes, if we put infinity, e to the power minus lambda x will become e to the power minus infinity, which will be 0. So that if we put infinity, that term doesn't come out. If we put 0, since we have x into e to the power minus lambda x, this will again become 0. So this first term, this entire first term actually reduces to 0. We do not need to take that term. So we just have the second term, it is 1 minus lambda integration 0 to infinity to the power minus lambda x dx. This becomes infinity to the power minus dx. If we do this integration, it becomes e to the power minus lambda x by minus lambda, and the limit will be from 0 to infinity. So if we put that limit, when we put infinity, again this term becomes 0, and if we put 0, this term becomes minus 1 by lambda, and we will have 1 minus sign before. So together it becomes 1 by lambda. So we can see that the expectation for exponential distribution is given by 1 by lambda. So basically what we see is mu is equal to 1 by lambda, or we can say lambda is equal to 1 by mu. So if you see the options, option B is given as lambda equal to mu inverse. So this is our desired relation. So for expectation of exponential distribution, we got 1 by lambda, which is also mu. So basically the expectation of exponential distribution is given by 1 by lambda, where lambda is the parameter of that exponential distribution. So this is how you compute expectation for any distribution. We computed it for exponential distribution. You can compute it for any distribution like normal distribution or Poisson distribution. Anything you can take and you can try to compute the expectation like this. Now let us move on to the last problem for today's session. Here also we are taking the same exponential distribution, px equal to lambda e to the power minus lambda x if x is greater than equal to 0 and the density is 0 otherwise. We have to compute the variance of this distribution. So in the earlier problem we computed the mean of this distribution, and now we are going to compute the variance of this distribution. So these are basically two major moments of any distribution, mean and variance. So you may all know that variance of a variable x is given by the expectation of x minus mu square. where mu is the expectation of that particular random variable. This is the general expression for variance, expectation of x minus mu whole square. But we can simplify this expression, and we have one more expression that is more commonly used, expectation of x square minus expectation of x's whole square. So, we can first see how we get that expression. So, this is simple. If you simply expand this square term, it becomes x square plus mu square minus 2 mu x. Now, if you take the expectation on each term, first term becomes expectation of x square. Then you have expectation of mu square. Mu square is already, mu is the expectation, so it has already become a scalar number. It is not a random variable anymore. So, your expectation of mu square will be equal to mu square itself. And the last term you get 2 mu out, and this is expectation of x. Again, expectation of x is mu, so this term becomes 2 mu square. So, if you simplify, you get expectation of x square minus mu square, or you can write it as expectation of x square minus expectation of x, which is mu whole square. So, this is the more generally used formula for computing variance, expectation of x square minus expectation of x's whole square. Now, we have already computed the expectation of exponential distribution. As you saw in the previous problem, the expectation of exponential distribution is given by 1 by lambda. So, this term we already know. Expectation of x is 1 by lambda, so this is 1 by lambda square. We have to just compute the expectation of x square. Let us try to do that. Expectation of x square, that will be equal to, again, integration minus infinity to infinity x square px dx. And the expression, let me write it down on this page. Px is lambda e to the power minus lambda x if x greater than equal to 0 and 0 else. So, here also x can take values only greater than or equal to 0. So, our limit reduces to 0 to infinity x square px is lambda e to the power minus lambda x dx. So, as you can see, we will have to go by integration by parts again. So, we will keep lambda out. Then here we take x square is the first function and e to the power minus lambda x as the another function. So, the first term will be minus, the second term will be, we have to take the derivative of x square and integration of e to the power minus lambda x. So, this is the expression. Now, again in this term, if you put infinity in place of x, again you get e to the power minus infinity and the term becomes 0. Also, if you put the lower limit 0 in x, since we have the term x square, this term again becomes 0. So, this term completely vanishes, this is equal to 0. So, the term we have is dx. The lambda also cancels out and minus becomes plus. So, this is the final expression. Here also we can take the 2 outside. This. Again we have x into e to the power minus lambda x dx within the integration. So, we will again have to do integration by parts. Here we will take x as the first function and e to the power minus lambda x as the second function. So, this will again become this. This is same as the previous case. So, the first term here again will reduce to 0. If you put infinity, this is 0. If you put 0, this is 0. So, this again becomes equal to 0. So, the term we are left with is okay. Now, if we do this integration, we get which is equal to, if you put infinity, this is 0. If you put 0, this is minus 1 by lambda, minus minus becomes plus. So, this is 1 by lambda. So, you have 2 by lambda square. This is the expectation of x square. So, expectation of x square for exponential distribution is given by 2 by lambda square. Now, the question was to compute the variance of this distribution, and we derived the expression for variance as expectation of x square minus expectation of x whole square. So, if we put the obtained value in this expression, so expectation of x square we got 2 by lambda square minus, in the previous problem we got expectation of x as 1 by lambda. So, expectation of x whole square becomes 1 by lambda square, and if you compute, the final answer becomes 1 by lambda square. So, the variance of exponential distribution is given by 1 by lambda square. So, we have computed the mean as well as the variance for this particular distribution, which is the exponential distribution. You can similarly compute the mean and variance for any other distribution. Okay, so these were the problems for today. If you have any questions, you can ask in the chat box. Okay, so I don't see any question in the chat box, so I think it is clear to everyone. So, we will close this session today. We will meet again in the next week, and next week we will be solving problems on non-parametric estimation of probability density functions. Okay, so let us meet in the next week. Goodbye guys.